Hello everyone, I'm Denis. I am a PhD student at LAM. My Twitter handle is den_sh. So a few words about me. I'm actually originally born in Ukraine. I'm not going to give this talk in Russian or Ukrainian because my technical Russian and Ukrainian is basically English words mixed with Russian interpretations and stuff like that, so it doesn't quite work. So as I said, I'm a research assistant at EPFL. I work at LAMP with Martin and the rest of guys that work on Scala-Offheap. You might know me from one of my previous projects that I worked before throughout the years while staying in Scala community. For example, I'm the original author of Quasi-Code shipped into 11. I'm a co-author of Scala Meta with Eugene Bermako, and my latest open source project that is available for public use is Scala-Offheap, and that's what I'm going to talk about today. Generally, I would describe my idea, my kind of vision for improvements in Scala that I make is to make lower level code possible, feasible, and actually approachable for general use. So you don't have to jump through the hoop if you really need some kind of special low-level support for some particular feature. So if you want something like this, just ask me and maybe I'll see what can be done. So today we would talk about memory management. We would quickly jump through a general overview of how generational GC works. We would quickly go through typical codes of garbage in Scala, and lastly we'll very quickly just overview with Scala-Offheap is and how can it help you with this. So most of the GCs available on JVM ecosystem are built around this idea of generational typologies, and basically says that it has a very complicated mathematical definition. I will not give you that, but basically what it means is most objects die young. So you allocate all the garbage, it doesn't live that long, and in fact it doesn't have to be so. And whole GCs are built around the idea. So very oversimplified view of how a modern Java GC looks like, your average typical Java GC. So you have two generations. Structure of this generation can be more complicated internally, but as a whole you have like two independent blocks called young generation and old generation. Whenever I say new or you accidentally use of many Scala high-level features, you allocate objects. Objects allocate pretty fast and they allocate in young generation. So GC is really tuned for having a very fast allocator that gives you allocated memory immediately. Throughout the lifetime of an object, it might survive a number of minor GCs. So minor GCs is a short scale GC that only works in young generation. And these ones are fine, they don't take that much time, they work on a small subset of a heap, so hidden is also the case, so it's not too bad. But if an object survives more than a bunch of generation, like when I say bunch, I mean more than number of generations specified in VM settings or environment or heuristics and so on and so forth, it gets tenured, like promoted to an older generation. And whenever that happens, it's better be a long-lived object because garbage collection in old generation is really expensive. Whenever you do full GC that collects both young and old generations, you are actually traversing basically a whole heap. So for example, if you have 10 gigabytes of memory allocated, you need to traverse 10 gigabytes of memory. And that's really expensive, like that's seriously expensive. And in this way, I would like to compare like modern GCs with a bank. So when you allocate to come for a loan, you get money immediately, like straight from the bat. You just sign some minor papers and you get lots of money and you're like super happy. Oh my god, it was so fast, you know. Then you start spending money and life is good. Until suddenly GC pause happens, you know, payback time. And you never know when this happens, unlike with a bank. So it can happen today, it can happen tomorrow, you know. You're always living on this edge of not knowing when it will happen because it's totally heuristic based and you have very little control of it. So how do you survive in this kind of environment if you want to write high performance code that can't really pause? For example, if you're handling a financial transaction that can't really pause here, that really has to respond as fast as possible. So you would like to make sure that GC doesn't happen in this particular period of time. So GM is not a simple question. So it's actually a very, very large area of research and development and best practices, and I would like to talk a bit about today. So quickly, I would just like to list a few common sources of garbage on Scala. These are not all sources, so you can definitely find more, and this is just a few that I would consider a bit surprising if you don't know about them, and they can actually hurt you if you don't know about them. So first of all is closures. So whenever you write any high-level code in Scala, like you just say array.map, you pass a closure. Closure is an object, so whenever you have a closure that's passed to a function, it always allocates. So it's actually an important thing, because for example, if you're writing super high-level code with monads and whatnot, with cats, shapeless, Scala, whatever, it's actually quite common to allocate hundreds of closures per simple piece of code. So this is something to think about. Then the second best thing is boxing. So Scala has erasure, so it means that unless you explicitly mark type parameters and classes and methods as specialized, you get array semantics. And what it means is whenever primitive escapes to a generic context, it gets wrapped into allocation. So if you pass something to generic context, it can be a method call, it can be a store an array, it can be different things. You create an allocation. So another thing is implicit classes and implicit defs. You most likely create allocations there because unless you use value classes, so please use value classes, okay? Then you have vars. Every single var core allocates an array just wrapped into a sequence, so like two allocations that happen to store your variable argument list. And lastly, we have the useful ones, the ones that corresponds to our actual domain. For example, it can be objects that belong to users and like whatever kind of services you try to model. So the last ones are sort of good. So everything else is surprising, accidental, or complexity. So it's not really, it's quite small, I would say. So I try to make it bigger. No? No? Okay, so I will just say what it says, and it's really unfortunate because this is really bad. But it basically, what it says array with fill with length 100,000. Okay, so large array. This filled with number 9 repeatedly, and then we just do map on this array twice. So now the question is, what's the type of object that will dominate here, or a performance kind of array? Okay. Any other ideas? Closures. Okay, good. What else? Okay, let's just start. What else is allocated here? So both arrays and closures are allocated here. Box of integers is a very good guess, but you'll see why you're wrong soon. Yeah. And lastly, you also actually have array wrapper, so basically this implicit classes I talked about. So arrays in Java don't have this nice map and flat map and whatnot. So actually array.map is implemented on an implicit class that wraps array. So it actually is a potential, not a potential for allocation. So now let's actually see what's going on, because it's really fun to guess, but you never guess right. Like I promise you, most of the time. So we have the same code. Here it's possible to make it bigger, and you can actually see it. It's nice. That's nice. Okay, so it's the same code that we just had on the slide, and it's actually visible. Can you see it?
Yep.
Okay, cool. So what's going on here is this workload is a code we put on the slide, and we just call it repeatedly in a loop to just force basically whatever it allocates, because it's in a loop, it will happen many times. So typically this workload part is your hot pass, basically your part of code that's actually important and does some work, and you can't really change it or remove it. So now what we're gonna do, we're gonna run this. Okay, okay, excellent. It's doing something. And now we're gonna look at it in JVisualVM. I'm not quite sure that I can make stuff bigger here. But here we attach to this thing and we use sampler profiler. And we see that there are no boxes to be found at all. Thanks. So there are no boxes to be found, so whoever said array was right. And everything else is basically negligible. Any ideas why no boxes to be found?
Scala understands that no boxing, there are boxing on boxing.
You wish. Any other ideas? Okay. So the reason is JVM, like primitive box types. When you say box type that value of, it actually has a cached array of instances for small numbers. And here we have a small number 9 that is cached. So basically what we're doing here, we're doing 9 plus 1, which returns 10, which is also cached. And then we do multiplied by 3 and it's still cached, so no boxes allocated at all. So you see, like, I would probably, like, first time I wrote this, I guessed it will be boxes, and I was wrong. It was really surprising, yeah. So now let's change it, like, now we know about value of, let's say large number here, not 9, but 9. And so here it's actually quite different. This one we don't need anymore. Yeah, SVT. So this one has large numbers, so this is basically what I originally sought to show, to illustrate boxing. But yeah, fun. And here we actually don't see, yeah, we see Shabalin integer. It hops back and forth because we have a part of time when you sample inside the maps and part of time when you sample outside of maps. So it's a sampling profiler, so you can still have slightly erratic behavior, but it's so much more clear than what you would get if you would guess. Okay, let's move on, number 2. And now, it gets more fun. We changed array to list. What will dominate now?
Cons, please.
Yes, cons. And it will so dominate that everything else will not matter at all. So, whatever like boxing issues we had is nothing. Now we have mostly columns, and columns actually are allocated more than integers. So for example, if you would want to optimize this code, you would not try to optimize integer first. You would actually try to see if just removing the columns is enough. Here, if we just look at how much time does GC take, because here we actually create obnoxious amount of garbage. We see that really garbage collection takes around 10% of our time. So for example, if it's an HTTP server, it means you're losing 10% of requests per second, so it's pretty bad in fact. And yeah. And the worst thing about GC pods, of course, is that you don't really get them spread out evenly, so some clients will get really slow performance and some will be fine. So hopefully I convinced you that like guessing is not a good strategy for this kind of issues. So seriously, always measure performance, never guess. So the only thing that can help you, like your knowledge of what's going on, is to explain why result of measurements are the way they are. It's really, really hard in the presence of very complicated optimizing compiler to guess correctly. And we didn't even cover kind of optimizations that JVM does to eliminate allocations, like it does escape analysis and stack allocation. So for example, if it would smartly know that this object doesn't escape, it would allocate on stack or even move it to register. So we didn't even discuss that part yet. So it's really complicated. Just don't try to guess, profile, and see what's going on. So hopefully now we know that like, so we get this situation. So we profiled, we removed all of the accidental allocations. So we don't have closures, or they do not matter. So both are fine. We do not have boxing, we do not have implicit decorators, we do not have vars. So we profiled and we know that none of these evil things hurt us. But now we're actually left with proper workload. So whatever our application is doing is actual true allocations that we are using. So we can't really just optimize them away because they're an actual work of our service, for example. You know, and some people just say, come on, it's not that hard, just tune some VM flags, just like pop them over, just like read all this documentation, and this is just one page of like 5 of VM flags. And some companies like Twitter have engineered basically just tune flags all day. And then when tune doesn't work, they fork JVM and then just make their own flags, you know, just fun with flags. So basically, what is kind of, how this makes me feel is basically this, so yeah. So just, now if you have pain, just take some painkillers. Don't try to remove the source of the pain, just take some painkillers and it will go away, definitely. So, and the worst thing about like just relying on kind of some happy path on GC is that you can actually probably make it work. You can optimize flags for your app, it will be fine. You will meet your CLA requirements on latency and whatnot, and so on and so forth. But what happens when your app changes? You need to retune again, and again, and one more time after that. Because, like what Dimitri said yesterday with collections, if you just pick some optimal collection now, how do you know that it's still optimal later when your code changed? The same here with flags. It's really, really hard to do them. Even if you can do them right, it's still hard, and it's not really maintainable. So, what I think is kind of more maintainable approach to kind of having fast and more or less deterministic code is my project called Scala-Offheap. Of course, I will say it's the best thing ever, right? I mean, I'm the author. So, the idea of Scala-Offheap is to basically say we are not playing by GC rules. We're not gonna try to, you know, bargain with GC, so kind of like try to configure it, try to make it happy, you know, just make sure it's like it has everything it needs. We're not gonna do that. So instead of doing that, we'll just have our own thing separately that GC doesn't know about and can't even look at. So from GC point of view, off-heap memory is just opaque blob of memory that is basically just, it cannot garbage collect it, it doesn't know anything about it. And this gives us freedom to do whatever we want there. And we know that whatever we do there, no matter how much memory we allocate there, we'll only see performance issues if our personal code is wrong. But it's actually, in fact, possible to not do GC and have reasonably sane memory management strategy. And this memory management strategy is called regions, but it's this next slide. Okay, let's start with this one. So basically, in off-heap memory, you have two types of allocator at the moment. You have malloc, where you can say malloc and free manually. So you, typical C-style malloc and free. If you need something forever, you can just malloc and never free, that's fine. But the issue with this is that you really need to kind of handhold every single allocation, so it doesn't quite scale to any non-trivial code. What does scale to non-trivial code is regions. What region is a specially annotated block of code where you essentially do this thing. So you say, I would like this piece of memory, I would like to allocate it in this piece of memory as long as this block exists. So if your execution is still in the block, your memory is allocated, you can still allocate it inside of the region as you go. And when you're done, you deallocate all of it at once, immediately. So you don't micromanage a single allocation, so you only manage regions, it's much easier. So for example, an example of region in a typical app would be HTTP request. So you say that you have one region per HTTP request, you allocate all of the garbage, of your domain-specific garbage, that we can also remove away in a region. Allocation is fast, it's about GC level, and the allocation is basically free. So unlike GC, we do not really have this bank loan situation. So when we allocate, we don't really need to worry to pay back the price sometime in the future, because we know that regions are kind of more level abstractions, kind of because we let Node's memory management system to know what we're doing. We annotate in code with some domain-specific data. You can actually do a much better job at freeing the memory. Now, what can you allocate in this stuff? Because it's a separate piece of memory, as we've seen before, that has nothing to do with GC, so you cannot allocate regular classes there. What you can allocate there is this specially magic things called Offheap classes. There are two types of classes. The first one is defined with addData. You can think of addData as a Offheap case class. It really very much behaves like a case class. So you say addData, like I know, person, name, surname, and what it is, in fact, is a very, very simple thing. It's not nothing as complicated as JVM class. JVM class has an object header. It's there no matter what's going on, and depending on the VM, it can be either 64 bits or 128 bits. It's actually memory for every object, even if you don't have any fields. Here, you just have a pointer to only the fields you have. So essentially, it's a C level abstraction, so it's not JVM level abstraction. Additionally, you have this add variant. What add variant lets you do, it lets you define essentially a sealed hierarchy of data classes. So for example, like enums in Rust, if you've seen that, or in Swift, it's a very similar feature. And lastly, we have Offheap arrays. Offheap arrays have all this common operation implemented in them, like map, for each, and so on and so forth. The implementation of these things is actually a bit more smart, I would say, than what we have right now in standard library. It uses macros and it inlines everything. It inlines closures, it inlines closure calls. It just generates code you would have written in your help with while loops. So now let's just have a look what will happen if we just rewrite our previous code, not visible here, but visible over here. Rewrite our previous code with Scala-Offheap. So it adds a bit of boilerplate, but this boilerplate is once per application. So this part is basically a configuration, basically VM flags if you want, but we only have 2 flags, so it's very simple. Once you have the configuration, which is called props, which is basically properties, you can actually write your code. And here what's going on is the same, basically the same code. It's also array.fill, also you're doing map, but here, think here, it doesn't allocate a single wrapper, it doesn't allocate a single closure. It just generates a very, very low-level code for it. And essentially, the code from before is almost the same apart from this part. So we have this magic region block. So what this region block says is that we would like some memory region that would leave as long as we are doing processing of workload. And important thing is that we cannot really move this region inside of a workload because we are using a result of a workload. So to reference the pointer, you need to have a region still open. So it adds just a little tiny bit of complexity, but you need to understand this is basically once per HTTP entry point. Basically, you define this kind of boilerplate once in your code, and then all you need to have is this implicit region passed around. Then everything else is just a simple, regular-looking code. Now, if we just run it, what will happen? So now, what we see is actually a very interesting thing. We still have allocations, but they're not because of our code. They're because of the print line. So we have this neo heap chart buffer popping up, and in fact, our benchmark right now basically benchmarks print line, essentially, in terms of memory usage. Because we ourselves don't really allocate anything. The only allocations we do on our side is this pool region thing. And it's really one allocation per transaction, effectively. So it's really nothing compared to what we had before. Okay. Okay. So, if you're careful, if you profile, if you use Scala-Offheap, you can actually remove all of this. You can actually remove all of this and remove it from a critical path. So it's important to know that there is no need for remove it, like to write everything with Scala-Offheap. That would be madness. Because Scala-Offheap is essentially a tool to optimize your tight spots. It's not your average, everyday kind of memory management tool. So in the end, what's kind of expected to happen is that you get to this place where there is no garbage and no pauses, and you're kind of like chill and just happy with your life because your latency is not an issue anymore. So to sum up, kind of a few things that you kind of want to remember from stock, if anything. Don't allocate garbage and performance-sensitive code. That's sort of obvious. And allocation is not cheap. So people say that allocation is free, but it's free only at the time of when you get the loan. You have to pay back later. Second, you always need to measure. If you want to write performance code, like you must measure. Because if you don't measure, you're guessing. If you're guessing, you're not guessing right. And lastly, if you have issues with having too much allocations of domain-specific stuff, you can use Scala-Offheap. It's quite easy to use. It's quite high level. You only need this kind of region allocation, region annotations here and there, but they're quite lightweight. Okay, and I'm done. Any questions?
Yeah, I have a question.
Yeah.
How does this region block play with asynchronous code like users and actors?
That's a very good question. And so the thing is, you need synchronization somewhere, right? So Scala-Offheap is not just synchronization, doesn't really give you any synchronization. So if you want to access the same memory from different places, you need to make sure this is safe because Scala-Offheap is not thread safe by default. Okay? Allocation is thread safe. Memory accesses and writes are not thread safe. So they are like normal, non-volatile fields in Scala, basically. Okay? Does this make sense?
Okay.
I have another question.
Yep.
As far as I understand, your library does two things. It manages buffers of heap memory, and
Right.
it lets you map some limited data types to the buffers of memory.
Right.
Then I use only the second part, for example.
Absolutely. Absolutely.
Okay.
So both parts are kind of interchangeable. You can just use allocator, and then you have like, if you're really hardcore, all this is built on Sunmis unsafe. Unlike what was claimed before, it's not going away, so don't worry. So in unsafe, you have this allocate memory, and you have this, a lot of methods to read and write from memory. So this is what is used as the backend for Scala-Offheap. You can use regions as an allocator for Sunmis unsafe managed memory, essentially. So it's absolutely fine, and if you want this kind of super low access, it's possible. So Offheap classes and Offheap arrays are absolutely optional. Yeah.
Can you have pointers from your Offheap memory to some managed object?
No. And the reason is GC does not like, the whole point of Offheap memory is to make GC not know about it, right? We don't want GC traversing our memory because then we'll have the same issues as we had before. So you cannot use direct pointers. You can always encode stuff. You can have some kind of array, and then you can store indexes to array in Offheap memory, for example. But you cannot have a direct pointer, so this is not allowed. Yeah.
What we have will be if we in the code try to allocate more bytes than we allocate to radio.
So that's a very good question. So I'll just quickly show you how regions work under the hood, very quickly. Okay. So it's actually a bit more sophisticated than what I told you, okay? But don't worry. So on top we have system memory, which is basically malloc-free kind of interface. Then you have a memory pool, which is an intermediate layer between regions and real memory. The reason why we need a pool is because this is actually super slow. Allocating through an actual basically malloc-free interface is quite slow. And we actually want to do basically memory management completely ourselves. So what we do, we allocate large chunks of memory. They're called chunks, these ones. Then we slice them up, and we make something called the virtual page. The virtual page is kind of our own, not operating system, a virtual page that lets us build regions as kind of a dynamically growing list of pages. So essentially, for example, if you go, like, when you create a region, you always allocate a single page. So you cannot allocate, essentially, a region pre-allocates one page at a time. If you go over the size of the page, it just asks for one more from a pool. When the region is done, it reclaims pages back to the memory pool. And memory is recycled, so you never need to worry about this being a bottleneck, because this is done just once. Essentially, the amount of allocations from system memory are proportional to your peak memory use. That's it. So, to answer your question, regions grow dynamically. This is how they grow. Yeah.
And then, what's the sense of the props in this case, if you grow the receiver?
So, it's actually possible to do your own regions that work differently and have the same interface. So, if you start, like, basically props abstract or implementation of a region. So it not only stores settings, but it also wires this nice syntax to an actual underlying implementation. For example, if you want to do your own super cool regions, which are better than this, but please tell me if you do, because I'm really interested. So if you can do better than this, you can actually implement your own props with your own configuration and your own underlying backend implementation. So it's actually quite easy. Yep.
Is the memory clear when it's recycled, or do you have potential for leaking memory from some other things that you're thinking?
So memory leaks. Okay. So memory leaks come in two kind of flavors. The first one is malloc-free, and if you use that one for anything but forever memory, kind of, you just allocate once and use it forever and never free it, you probably have a memory leak somewhere. So never use malloc-free and expect to free from time that. You will most definitely make a mistake. Regions allocate stuff in pools, and pools persist as memory they had. So, for example, they persist up to your peak usage. So, for example, if your peak usage is 16 megabytes, they will persist as 16 megabytes even if you don't have any region open.
Yeah, but the question was not really about memory leak, but the content of the memory area. Is the area of memory clear when you recycle it, like you do?
So, depending on the implementation,
I see. Zero.
Yeah, I see what you mean. So, depending on the implementation, so as one of you said, is that we have two parts, basically allocators and everything else, which is high-level features built on top. So, high-level feature decides if it wants to clear memory or not. So, arrays, for example, clear memory, of course. Yep.
So how is it technically implemented? Do you modify bytecode?
No. So data and variant are macro annotations. They use macro paradise plugin, but it's actually quite fun. Like this macro paradise, you should actually try it. Arrays are just normal macros. Are just normal regular macros that you would kind of write in Scala to 11 or to 10. They are like nothing special, so they are really just macros. Everything else, which is basically this, is implemented in runtime as normal code, basically. So if you don't like, all of the high-level features are basically macros, and all of the allocations and runtime management is just normal Scala-looking code, just nothing special. Yeah.
What do you use in GVM to allocate memory manually? What API provide? What API GVM provides you?
So as far as I know right now, your only officially endorsed way to allocate memory and sort of work with it is Java Neo byte buffer. Everything else, like SunMist-can-save, is actually not supposed to be used as alphabet. So SunMist-can-save, even though like it's very controversial API because everybody uses it, like everybody. If you just take any decent large framework that kind of deals with high load and stuff, like everybody uses some stuff from SunMist-can-save. And at some point, Oracle really wanted, like, this is really unsafe. We need to remove this. Let's just remove it in Java 9 without deprecating, but just remove it. Just don't worry about bringing everybody else. But we will tell them in advance, and they'll have to not use it again. But that didn't work. That didn't work because there is no replacement for unsafe, because Byte buffers are not quite the same. They are bounce checked. So if you don't want bounce checks, if you want to do your own bounce check or like whatever else you want to do, you cannot do this with byte buffers. So byte buffers are really good for serialization, but they're not so good for everything else. Any more questions? Okay, so I think we still have a bit of time, so I'll show you a few slides that I have extra. So this is an example of benchmark over Scala-Offheap versus a GC. So this is a picture of typical benchmark for GCs called binary trees. So it's, in its spirit, it's similar to what we've seen before with doing some workload in a loop and allocating a lot of memory. It's something like this. But it allocates binary trees and not lists or arrays. So now we see 3 lines here. So upper one is Scala-Offheap with special debug mode that lets you be safe, absolutely memory safe. So it checks additional stuff, it makes sure that you close regions, make sure that you can also open regions manually. It makes sure that you close regions, make sure that you cannot reference stuff that is not in an open region. So it's like super safe. So it's basically as safe as GC. And then we have unchecked mode, which is a tiny bit less safe, but not nowhere near as unsafe. And it's a lower line over there. And then in the middle, actually in the middle, I mean this one that goes to the middle, is GC. And what is not quite clear here, you can actually also have this kind of dotted lines around every single solid line. So for example, for GC, I'm just kind of like showing you where it goes. So you see, as you get closer to full memory size, basically a full memory capacity of your current JVM, you start to get crazy spread of performance. This is basically an issue that kind of makes Scala-Offheap necessary. Is that here, you can get, depending, like for example, if you have, again, our run example of HTTP server, if you have HTTP request and you're handling connections and so on and so forth, so depending on luck, user will either get something from over here, basically from our unchecked to our checked, and then basically just luck. So for example, if a critical customer comes and asks for something, he might get results slower than some random guy. For example, you have absolutely no control over this. And lines for Scala-Offheap are essentially just basically solid lines. There is no dotted lines in fact, so they are essentially just one line. So there is no spread in performance whatsoever. So it's nearly deterministic because our management is basically designed to be nearly deterministic. And Scala-Offheap here is essentially the best case of GC on realistic heap size, but it doesn't have a spread, so it's always best case. So it doesn't get to be that much faster on average. So if you just look at the lines, right? So lines are averages. So if you just look at the line, it seems like it's almost the same, right? With benchmark, like these two unchecked and GC look almost the same, right? They just one a bit harder, but like the average never tells the whole story. And here the whole story is extremely important because we care about latency always. At least I care. For example, if you have an editor and like how many times, like does anyone here use Eclipse? IntelliJ?
Yeah.
Yeah. Okay. Cool. How many times does it randomly freeze and you cannot do it like for a second, anything for a second or so? Okay. So I hear some laughs, so like I assume that like this happens, right? This is basically probably a major GC. I mean, most of the time, because IntelliJ itself is quite low written. I've seen the sources. They try really hard not to cause GCs, but again, you cannot just not cause GCs. It's a constant loan. You just loan more and more money. You're bound to get hit one day, you know. And this kind of pauses are essentially what happens. From time to time, you get a worst case, and this is really bad. Another chart that I would like to show you is how allocations, so basically how fast can we loan money to people. So on left we have GC. It's quite a bit the fastest at the moment. So as I said before, GC is optimized for fast loans with PBX sometime in the future. So regions are just tiny bit slower, like minus 10% or something, like tiny bit slower, but basically negligibly slower. And then in the end we see malloc. Malloc is really slow. Malloc is horribly slow. So again, don't use malloc. Okay? It's there for special reasons, but unless you know that you need it, please use regions because they're generally much faster, as you can see here. Here is an example of our map of benchmark similar to our map we've seen before, only run in JMH with proper everything, and not in our hand-rolled simple app for demo. So as you can see, difference is actually quite dramatic. And there are basically two factors. Is that the first one is we inline everything and basically have a normal loop. So we don't have boxing, we don't have virtual codes, we don't have really anything about it. We just have normal while loop. If you would write the same while loop in a Scala and you compare it to Scala-Offheap, it will be the same. But if you write maps in both places, you actually get dramatic performance difference. And here, I think it's like 100x or something. So in some pathological cases like this, it can be really bad. It can be like, seriously, like, if you loan too much money too fast, then the payback is going to be dramatic. That's basically what it is. And this one has already been shown. Okay, cool. Thanks.